Hey there, class. We're here today. We're going to look at an example. Our example is a situation that is in equilibrium. So here it is. We have a meter uniform beam, has a certain mass, and it's supported at two locations as seen in the picture. All right, so here's our beam and uniform and a certain mass. Notice that there's a support, we'll call it support 1. It's over here, 15 centimeters from this end. And support number 2 is 25 centimeters from this end. Word uniform, okay, when I see this, what I'm thinking is that basically the mass is evenly distributed. So basically the center of mass, all right, the center of mass will be in the center, okay, or in the geometric center, right? It's in the geometric center. So the center right there. And of course, in our case, the center of this is going to be right here in this location. So that basically is at the halfway point, in other words, the 50 centimeter. All right. So what I'm going to do is I'm going to pause the video and I'm going to redraw my beam. Specifically, I'm going to draw a free body diagram. Now, this is something known as rigid body equilibrium. And since we're actually concerned about the torques that these supports do, we are going to actually treat the object as an entire object itself. So we're not just concerned about the center of mass. We are, in fact, concerned about the entire rigid body. Okay, so here we are. What we've done is we've drawn a free body diagram. And again, considering this is a rigid body, I am actually not treating these forces as they are acting on the center of mass. I'm actually treating them where they actually act on the object. So as in our picture before, these are set distances away from the ends. Let's recall some problem-solving strategies for this kind of problem. First of all, we need to draw a good free body diagram. That's what we've just done. Next thing we're going to do is we're going to pick a location as our point of rotation. All right. This doesn't actually have to be at a physical fulcrum. So in other words, if I look at my problem here, this beam would naturally want to rotate around 2 or 1. But I don't have to pick those points as my point of rotation. I can pick any point that is convenient. And we'll talk a little bit about that choice here in just a moment. Next, we're going to define our x and y axis. In this case, it's pretty standard. Up is going to be y, left and right is going to be x. And then what we're going to need to do here is use Newton's second law and our condition for rotational equilibrium. So let's recall those conditions. So we have the sum of forces in our x direction have to equal 0. The sum of forces in the y direction have to equal 0. And once again, we're going to be using our standard, we'll use our up and down as our y, and that is our x. So this again, these are the conditions for what we call translational equilibrium. The other condition that has to be met is the sum of the torques must also be equal to 0. And again, this condition must satisfy rotational equilibrium. All right, and for this problem, I'm going to call a rotation of clockwise as my, that's going to be my clockwise is positive. All right, now let's talk about the point of rotation. The point of rotation is often put in a place where it's convenient. And what do I mean by convenient? Well, when I'm talking about a convenient place, I'm actually talking about a place that would actually kind of cancel out a force or cancel out a torque. So I'm going to say, since this is an unknown and this is unknown, a convenient place to put my point of rotation is going to actually be at one of these locations. So this is going to be my point of rotation. Because again, the torque that the normal force 1 has about this point of rotation is actually 0 because it is right there. The distance from the point of rotation is 0. If I were to move this point of rotation somewhere else, of course, it would have a torque, and therefore we'd have 2 unknown torques in our equation. All right, I'm going to pause the video, and I'm going to write out my rotational equilibrium equation. Here we are. The again, strategy here is that we're going to take advantage of the fact that there is rotational equilibrium. The sum of the torques has to be equal to 0 because this thing is not accelerating in a rotational fashion. So basically, there are 3 forces acting on it. So potentially, there are 3 torques. So I've included those here. We have the torque due to the gravity right here. We have the torque due to this one right here, which again we'll see in just a moment is 0. And we also have the torque created by the beam 2, or support 2, and where that's going to cause this rotation in a counterclockwise direction, which again is going to be the negative direction that we've defined. Now again, this is key that we understand that these directions, or sorry, the distances are from this point of rotation. So we notice here that the distance for 1 is actually in fact 0 meters because it is directly at this point right here. Our FG will be measured from the point of rotation to here. Now keep in mind, this entire beam was 1 meter. If we take 15 centimeters off, again, this would be 50 centimeters here. So we're going to subtract out 15, and what are we going to get? I guess we'll get 35 centimeters. All right, and then from here to here is going to be, let's see, it was 25 centimeters from this side. That means this distance in here would also be 25. So I guess we're going to take the 35 plus 25, and that would give us, what, a 0 and 60 centimeters. So that means the distance to the center of gravity is going to be, what was it, 35 centimeters. And the distance to support number 2 is going to be 60 centimeters. All right, now let's go down back to our equation and kind of finish this up. So once again, the torque at 1 is 0 because, again, the distance is 0. So I'm going to just cancel that out right now. We're going to have the force of gravity here times the distance to the center of gravity, or the center of mass. And we're going to subtract out the force, this is force 2 times distance 2. And these, of course, have to equal 0. My goal was to find the force 2, so I'm going to actually do the algebra to isolate it. So again, my goal here is isolate F2, so we're going to solve for F2, and that is going to give me, what is it going to give me here? Let's see, F2 would end up on one side, and then on the other side we'd have, I guess, what, FG times DG divided by D2. All right, so I'm going to pause the video, I'm going to implement this strategy, and we're going to solve for F2. Okay, so one thing, a couple things to take care of here. Of course, Fg, the force of gravity, is found by taking mass times the gravitation constant here on Earth, and that, of course, comes into play right here. The dg and d2 were 35 and 60 respectively. A couple things other to note is that we wanted to convert. Initially, we remember here that we had things in grams and centimeters. Again, just a good habit to get into, convert everything. This part over here where we had the dg divided by d2 wasn't entirely important that you converted because, again, it is a ratio, and no matter if you converted it or not, it's going to give you the right answer. However, again, I like to always just convert to make sure that that's just something you think about. All right, did my math and ended up finding the force 2. That's this support force right here. I guess I called it Fn2 before, is going to be the 2.8 newtons. Now, the other part of the question was to find the support forces, where that was this normal force here and that normal force here. We've just found this Fn2. Now our goal is going to be to find the Fn1. So we could reset a point of rotation somewhere else. Now that we know both of these forces, setting the point of rotation at another place, doing the whole translational rotational equilibrium would work. However, I'm going to say that the easier method here might be to look at the fact that because we know this is a rigid body equilibrium, we know that the forces in the x direction and y direction have to be equal to 0. And I think a better approach here would be to, now that we know one upwards force and one downwards force, all we have left is to figure out the this last upwards force, which again is going to be a net force equation. And I will go ahead and do that in my strategy, and we'll pick up in just a moment. Okay, so once again, I'm going to use the net force equation in my y direction. I know that they have to kind of all balance out. And so my sum of forces in the y direction has to equal 0. There are 3 forces that act in the y direction. In fact, there's only 3 forces in this problem altogether. So my normal force in the upwards direction, there's a normal force 2 in the upwards direction, and then there's the gravity force downwards. That's why it's negative. And I'm going to basically end up solving this for, I guess I'm solving it for this one, right? So I'm going to solve for Fn1. And it wasn't consistent with my problem earlier. I called this F2, but of course we're really dealing with the normal force. So I'm going to go ahead and pause the video again. I'm going to do the algebra here to isolate my Fn1. I'll substitute it in my implementation, and we'll pick up when I've solved it. Go ahead and finish this up, solving it for Fn. I'm going to actually end up with my gravity force minus the normal force 2. And as I go over here and solve that, I'm going to get, again, here's my gravity force, and this is the Fn2. Subtract them, and I get 2. Now, it does actually end up being about 1.9971, but to 3 significant digits, that's going to round up to. So my final response to the question is going to be that the normal force 1 is going to be 2.00 newtons upwards, and the force due to support number 2 is going to be 2.80 newtons upwards as well.